and welcome. Before I get started with my talk, I've been asked to deliver some important information. Now, in order to ensure that you remember this information, I'm going to tell you a little story. So, back in the UK, I was walking down the street one day, and I saw this character, and he was dressed from head to toe in camo kit. Okay? There was a chap walking along next to me in the street, didn't know him. He goes, "Hey, what's this?" And he bent over, so his body was like horizontal, and he ran full tilt at this guy, headbutted him in the stomach. And the guy in the camo's lying on the floor going, "Ah, what'd you do that for?" And this guy goes, "Oh, sorry, mate, didn't see you." Now, why did I tell you that? I told you that because the important message that I've been asked to deliver is that there is to be no camouflage clothing to be worn in Barbados, not even socks. So please can we adhere to that. So now let's get back to my talk. So I am a geologist, so I study all of the sciences and combine them to come to an understanding of the way in which the Earth works. In a previous life, I worked on oil rigs, and subsequent to that, I then was a teacher of geology for 26 years. And I now lead adventure travel expeditions and lead holiday tours. And I also collect and sell Cornish minerals. Cornwall. Cornwall, also a place with lots of pirates. So, I've got a question for you. What is a pirate's favourite letter of the alphabet? No, it is the C I love. So I thought I'd better soften the blow a little bit with some humour in that I now need to talk to you a little bit about plate tectonics. But I'm not going to apologise for that because it is absolutely fundamental to an understanding of the geology of Barbados. If you're a little bit confused because there's been lots of different angles taken on plate tectonics, if you go back to my very first talk, The Birth of a Theory about plate tectonics, that was born from 26 years of teaching geology. So it's clear, it's concise, it's precise, and most important of all, it's factually accurate. So, let's have a look at Barbados. A few things that I'm going to address during this presentation. First of all, why is Barbados considered to be the Castaway of the Caribbean, 160 kilometres away from the other islands? Also, we'll look at how nice, hot, sunny place with corals. We'll look at how evidence from fossil corals in Barbados provides us with evidence for past glaciations and also sea level change, and potentially for predicting future sea level change and climate change. We'll look at why Barbados has caves. Some of you may have seen in the excursions about there's a cave called Harrison's Cave. And I'll consider a little bit about water supply in Barbados and also oil. So, if we go back to the whole birth of a theory, the plate tectonics, you've seen versions of this slide many times. I've adapted it a little to try to make it clearer for you. What we've got here is a destructive plate boundary with subduction. But what nobody else has explained is the reason why, with two oceanic plates, which one goes under the other. Now, the reason is that the Caribbean plate here is older. Because it's older, it's thicker. And because it's thicker, it's more rigid and stiffer. So when we had the spreading of the Atlantic Ocean coming towards us from the east, that younger plate was thinner and less rigid, and therefore that is the one that has been subducted. And that is seen a lot more clearly when you look at a cross-section. So if we had, imagine what it looked like side on. So here we've got the South American plate being subducted, being destroyed. And again, a really important point that you need to remember is that when this happens at a subduction zone, it's not melting, it's partial melting. And that's critical. If it was melting, then the magma that you'd produce would just be the same as the magma that formed the rocks that are being melted. So from basaltic oceanic crust, you'd get more basalt. as we've all been saying, the volcanoes in the Caribbean are not all basalt. They're of a much thicker, stickier kind of magma, which gives you very explosive eruptions. So it's this partial melting of the basaltic oceanic crust together with the wet sediments on top, which are quite rich in silica, that produce a magma with more silica in it than a basaltic magma. It's referred to as andesitic magma. Clue if it's where it was first studied, the Andes. So that all of those volcanoes along the west coast of South America, they are explosive stratovolcanoes, layers of volcanic ash and lava, very explosive. So this new magma, this andesite, is what gives us the explosive volcanic activity, and then this island arc parallel to the subduction zone and this deep trench where the crust is being destroyed. So this is how we got the Antilles volcanic island arc, with this partial melting. Now, you'll notice on the diagram that you've also got here the East Caribbean Oceanic Trench. This is a very deep oceanic trench. And what's significant when we're looking at the history of Barbados is that this deep trench was getting infilled from the south. So one of the largest rivers in South America is the Orinoco River, and that reaches the sea coming out of the top of Argentina, and it's got an enormous drainage basin, a drainage basin of over 1 million square kilometres, and that means that it's carrying a vast volume of sediment, of sand and mud and silt and clay into the southern part of the ocean there, and that is filling in this trench, or was filling in this trench. Now, this went on for about 55, 60 million years. So you've got an enormous pile of sediments. So we're talking about maybe 18 to 20 kilometres thickness of sediments, all there in the trench. Now, because the plates are moving towards each other, yes, you've got the subduction and the creation of the red volcanic islands there, and then still on the Caribbean plate, you've got those green islands, which is where some of the sediment is being scuffed up out of the oceanic trench. What we're looking at with Barbados, though, is something a bit different, because if you notice, Barbados is actually 160 kilometres away on the South American plate. So this is quite a different situation. And it's a nice place to go. It's a safe place to be, because there's no volcanic hazard. No volcanic rocks there, and it's not on the boundary, so you're not going to get an eruption there. And it also is usually off the hurricane pathway. So how did it actually originate? Well, we've got our plates moving towards each other, and the pink there is all of this sediment, and it's being compressed, it's being squidged, and it's forming a big wedge of material. And this is known as the BAP. The Barbados accretionary prism. Accretion meaning sticking on. And this is how continents grow, is when you get these accretionary wedges of sediment being scuffed up. It can't be subducted, so it sticks onto the edge of the volcanic island chain, and eventually you build a continent. Now, if you get all of that compression, at depth, solid rocks can flow. Now, that sounds a bit hard to get your head around. So, bit of a strange analogy, but if you think of a glacier is made of ice, which is solid, and glaciers flow, and they may flow a few meters a day. At depth, solid, hot rock can flow, but we're talking a much, much slower flow. We're talking perhaps a few millimeters a year. But on a geological timescale of, we're talking here 55, 60 million years, that's a lot of compression and a lot of movement. Now, this compression then means that the rocks are being uplifted as well. Now, if the rocks get to a shallower depth, they're colder. And cold rocks don't flow. Cold rocks are brittle. So when they experience stress, when they undergo tension, or in this case compression, they will undergo what's called brittle fracture. They'll crack, and there'll be movement either side of those cracks. So you can get the crust either being extended or shortened. And these cracks in the rocks with movement either side are referred to as faults. So we've got a lot of deformation going on here. And over a period of about 10 million years, we had uplift of this Barbados ridge in what is known as the Scotland district. And over about 1 million years, this compression and uplift and the gradual accumulation, easy for you to say, accumulation of sediments, then led to the Barbados ridge actually popping up above sea level. So this is how Barbados actually formed. And this kind of accretionary wedge, you find them all over the world, but what's unusual about Barbados is the fact that it's actually made it to the surface. And the reason that it's done that is that enormous amount of sediment coming up from the Orinoco River. That is pretty much it on plate tectonics, folks. Moving on. I mentioned the Scotland district. So the Scotland district there on the eastern side, the northeastern side of Barbados, they're the oldest rocks on the island. They're about 55 million years old. And as I mentioned, these were being deposited. Yes, the sediment came from the Orinoco River, but they're marine sediments. They were deposited under the sea. So you've got some beds that would have been deposited quite quickly. So, for example, if you have a big flood, then you've got a high energy conditions, you've got a lot of coarse material, the river has the power to move larger fragments, so you'll get sandy material being washed out and all dumped in one go. So you get big thick beds of sand. Then the water all calms down, and the last stuff to be deposited is the finest clays. So you tend to get a bit of a repetition of coarse sand, medium sand, fine sand, silt, and then the clays. And this sequence tends to be repeated again and again and again. So we build up a big, thick sequence of rocks. Now, these rocks then had 55 million years, because they're the oldest rocks on the island, they had a long time to be deformed. So the deformation then, part of that was the compression and the extension that you get as a result of the plate movement. And part of it was because we had those hot, solid rocks being bent or folded at depth. And then when those rocks were uplifted and they were colder, they're still undergoing stresses and they're fracturing or faulting. So the yellow line on the image there is a fault, and then you can see the bending, the folding of the rocks as well. And because these rocks have undergone so much deformation, we can't see the base of this sequence. But estimates vary. We think maybe 4.5 kilometres thickness of sediments to make up this Scotland formation. So we've got the emergence of an island, and surrounding the island we've got warm, clear, shallow, tropical seas. Fantastic. I can't wait. Now, those are ideal conditions for corals to grow. They're ideal because corals have what's called a symbiotic, a mutually beneficial relationship with photosynthetic algae. So the corals, because the polyps sometimes can sting a little bit, and that might put off some fish from grazing on them, so the corals then protect the algae, but the algae, because they're photosynthesizing, are producing oxygen, which is beneficial to the coral. So we've got a fringing reef, a reef that's surrounding the island. But remember, the island is still being uplifted. And during some periods of time, the rate of the coral reef growth would keep pace with the uplift. So this means that about 85% of the island of Barbados is covered with coral rocks. Yes, underneath it you've got those marine sediments that were largely derived from sediment from the Orinoco River, but as Barbados was rising between about 500,000 and maybe 120,000 years ago, we've got a series of uplifts. So the uplift isn't constant, and that has a significant effect. Because the uplift isn't constant, what will happen is you'll have a period of stasis, a period when everything's the same and there's not much change. Then you might have a period where there's slightly faster uplift. The corals can't keep pace with it, so they get exposed above the sea, and of course then they will die, and a new coral reef will form a fringe around the island. And this cycle gets repeated again and again. So what we develop is a series of terraces, like a giant staircase, which is the profile of the island of Barbados. Now, the reason why we have these terraces is the localized uplift. So the localized uplift is because of the plate tectonic movement. We also have some of the clays that are in sediments below are very rich in water, and they're slightly less dense than the surrounding sediments, so they kind of rise up in what's called a diapir, a bit like, remember the lava lamps in the 1970s? So it's a bit like one of those bubbles kind of rising up through the surrounding rocks. So that also would have contributed to the uplift. But superimposed on that local relative change in sea level due to the uplift of the land, you've also got global changes in sea level. Now, those global changes in sea level can occur for a variety of reasons. We can have a global change in sea level, for example, if we have a period of glaciation. If a lot of the water on the planet is held in ice sheets, that means that the relative sea level globally will go down, which explains why at the peak of the last glaciation, you could have walked from England to Ireland, for example. Conversely, if things warm up, if we have global warming, as you heat water up, it expands. And that is the main cause of sea level rise relating to global warming that we have at the moment. And that thermal expansion of the oceans leads to a relative rise of the sea level, and that again is a change that we need to understand in order to predict the future. So, how can scientific studies in Barbados relate to the study of glaciation and global climate change? Well, as the Monty Python team would say, now for something completely different. See if you can spot the connection between this little video clip and... So, a little clip from the day after tomorrow. So what was the guy doing with a great big, looked like a corkscrew, didn't it? Big, what's called an auger, drilling into the ice. Well, if you go to the polar regions and you drill into the ice and you get what are called ice cores, they provide a lot of data, really valuable data, for interpreting climate change and sea level change. Similarly, if you take core samples from deep ocean sediments far away from land, you can get a lot of information. The information is largely relating to isotopes of oxygen. So in sediments and in the air bubbles trapped in the ice and in the shells in the deep ocean sediments of what are called foraminifera, tiny little fossils with calcareous shells, these all contain oxygen. And the oxygen isotopes, you've got oxygen 16 and the slightly denser oxygen 18. Now, if you have a very cold period, a glacial period, then you've got a lot of water on the land as ice sheets. And the oxygen in the ice will there be the oxygen 16, because that is the oxygen in the water vapor, which is less, the less dense oxygen, is able to evaporate and then will fall in the snow and then accumulate as ice to give you your ice sheets. Whereas the oxygen 18 is too dense, so it stays in the oceans. So if you look at the proportions of oxygen 16 and oxygen 18, if there's a lot of oxygen 18 there, then it was probably a cold period. If there is a more even quantity, if there's a lower percentage wise of oxygen 18, then it was probably a warmer period. So I've been talking about glacial periods. Well, it might surprise some of you to know that actually we're still in an ice age. We've been in an ice age for about 1.6 million years. What we're currently in, though, is an interglacial period. So this is where we hook in to Barbados. Each of those giant steps, each of those terraces, records the sea level at the time that the reef was formed. And by analysing the oxygen isotopes in those coral fossils, we can look at future potential sea level rise and climate change. Now, the most important study of this was of the first high cliff terrace. So this is a coral that was formed 125,000 years ago, at the peak of the last interglacial. So at this time, it was a pretty similar climate today, but the sea level would have been approximately 6 meters higher. And studies of this particular coral level, this coral terrace, have been, in some cases, they've been described as the Rosetta Stone, the key to understanding a lot of the climate change that we've had over the last couple of million years. And it was studies in Barbados that actually convinced climate scientists that the work of a Yugoslavian astronomer called Milankovic, who had studied the cyclic changes in the Earth's orbit, that he was actually right in his assertion that these changes in the Earth's orbit actually drive the oscillations within an ice age. Whether you have an ice age or not is something different. That depends on the juxtaposition of the continents. If you don't have continents at the poles, you cannot have accumulation of massive ice sheets, so you will not get an ice age. But if, through continental drift, there are large areas of continent over the poles, that is when you will tend to get the accumulation of large amounts of snow and ice to form ice sheets. And as that accumulates, you then have a sort of positive feedback loop, because the white of the ice will reflect the solar energy. So back to our man Milankovic. So he looked at these three cyclical changes. So first of all, the Earth's orbit is not circular, it's elliptical. And this elliptical orbit means that throughout a 96,000 year cycle, the amount of solar radiation getting to the Earth will vary. As the Earth is rotating on its axis, that axis is actually tilted. This is known as obliquity. And this again produces a cycle with a period, a time frame of 41,000 years. And then finally, we've got the fact that as it's rotating on its axis, it kind of wobbles, which is called precession. And that has, again, a different period. It's got a period of 21,000 years. Now, if you superimpose all three of these cycles, then you produce this Milankovic curve. And if you then plot on that graph the temperatures which have been determined using the oxygen isotope data in Barbados, you find a pretty good correlation. So you've got the peaks of the interglacial periods, the warm periods, and then the troughs of the glacial periods. Now, these corals also explain why we get these beautiful coral sand beaches. However, any of you who attended my gorgeous girlfriend Callie's lecture about beaches will know that actually these beaches are parrotfish poop. So, moving swiftly on. With all of this coral limestone, that coral limestone is very holy. And I'm not talking in a religious sense. I'm saying it's got lots of holes in it. And a lot of these holes are interconnected. And it's because of that that water is able to percolate, to soak down into the ground and to create caves. And this map shows those red dots are what are called sinkholes, conical holes, anything from 10 to 120 meters across. And this is where underground there's been some kind of collapse in a cave, and then the material has fallen into it to form this conical hole. Now, many of these sinkholes do have caves underneath them, and there are over 85 known caves in Barbados, including 3 quite long caves with underground rivers in them. There are very little surface water drainage. And these affect people. So in 2007 at Archcott, an unfortunate family died when their house disappeared, fell into a cave. And there had been no surveying of the extent of caves on Barbados. And after this, there was a lot of surveying of whether or not there were caves in Barbados. And they actually revealed that underneath the Canadian High Commission, there is a cave about 120 metres down, and it's only got one little pillar supporting it, which is a bit of a worry. So, don't worry if you're going to go down a show cave. The caves that are open to tours are very, very safe. I am quite passionate about caving. I also go mine exploring, but I have to say I prefer a natural cave any day of the week, more of which later. But you can go and see these awesome caverns with the astonishing, the stalactites that hang down, the stalagmites that grow up. So Harrison's Cave, then, named after an 18th century landowner who probably never even went into the cave. It wasn't really properly explored and mapped until 1974, believe it or not, by a Danish engineer, Ole Sorensen. So, the natural entrance was this Welchman Hall Gully. But the government decided that this cave was pretty spectacular and they could make money out of it. They could develop it as a tourist location. So they drove in a tunnel. You can see the Boyce Tunnel entrance there, which is the entrance that you would enter the cave by. And that's named after the guy that was operating the big tunnelling machine that broke through from outside into the natural passageways. They've even put in a lift. But I think it's much more fun to abseil into caves. So, 1981, 2.3 kilometres of this stream cave system became open to visitors, with all of these stalactites, the stalagmites, the pools, the waterfalls, and even the Great Hall Cavern, 15 metres high. Quite impressive. So you can go on a 1-hour tour in a tram, and every now and again you stop, you get off and look at little bits on foot. Or you can go on a 4-hour, more adventurous tour with headlamps and knee pads and all of that. And you're going into a cool, dark, subterranean world. And you're just as capable of having your breath taken away by the beautiful formations as you are from any beautiful beach. And it's a constant temperature, a nice, pleasant 27 degrees. So you're fine in shorts and a T-shirt. So how do these caves form? Well, the calcium carbonate that makes up the corals is quite reactive. When rain falls through the air, it will get some carbon dioxide dissolved in it. What's the significance of that? You may remember at school testing things with litmus. Yeah? Now, if you blow through a straw into a glass of distilled water, and then you test it with litmus, the litmus will go red. What does that mean? You've made an acid. So the carbon dioxide from the atmosphere dissolving in the rain makes a weak acid, carbonic acid. And this percolates down into the rocks and dissolves some of the calcium carbonate of the limestone. And this produces a very distinctive kind of topography, of landscape, called karst topography. And what's interesting about this, for me, is that means you've got lots of caves. Very little surface drainage, lots of sinkholes, and lots of underground caves. So we've got the cave system forming over hundreds of thousands, sometimes millions of years. And then you've got open passages underground. Then what happens is that as water percolates down and it's got this dissolved calcium carbonate in it, so you've got calcium bicarbonate, when it reaches open space, there's a lower concentration of carbon dioxide. So the carbon dioxide comes out of solution, a little bit of water is released, and what's deposited is calcite. And that calcite is what makes up your, what are called speleothems, your stalactites and stalagmites and so on. Usually they're white, but very often you will see them in a range of colours, typically going from white through cream to yellow, through orange to reddish colours. And this is due to small levels of iron oxides, rust if you like, and that's what influences the colour. I mentioned that as well as a caver, I'm also a mine explorer. In some of the mines in Cornwall, where they're copper mines, because of the copper, you will get formations in every possible shade of blue and green, which is truly spectacular. So, all of these photos that I'm about to show you of examples of these speleothems are from Harrison's Caves, taken a few years ago. So we've got the stalactites, the ones that come down, they include teeth atop, and they hang on tight to the roof. You've got the stalagmites, which include G for ground, and they might reach the roof if they keep on growing. And sometimes you do get a stalactite meeting a stalagmite to form a column. If you have water flowing down the walls, then you will get what we refer to as flowstone. If you've got water coming out from a long crack, you will get curtain-like formations. And if we have pools, then you will get material being deposited at the edges of those pools to form what we call rimstone. So you get these gower pools, which can be very, very pretty. But they're not the only interesting things in this cave. And Harrison's Cave do actually do a special tour so that you can get up close and personal with Molossus molossus, the fantastic scientific name for the velvety free-tailed bat. So they've got this adventure tour which is trying to dispel misconceptions about bats. You know, they're not all vampires. Some of them are truly lovely. There are other caves on the island. This one is Animal Flower Cave. Now, this is formed in a different way. This is actually a sea cave. You might remember from Callie's talk about coastal landforms, that if you have a peninsula sticking out into the sea, which has got some cracks, joints or faults in it, which are a weakness, and that gets exploited by waves chucking loads of rocks at it, and it builds in a cave, and that cave can eventually go through the headland to give you an arch. So this is an example of that happening. It was once at sea level, but due to the localized uplift of the land, it's now a few meters above sea level. You might notice out on the edge there that the white, that's all guano, which is bird poop. So on the cave floor, there you get loads and loads of sea anemones, and that's what gives the cave its name. Another cave is Cole's Cave, much less visited. It's quite difficult to get to. It's got steep, narrow entrances, very overgrown with vegetation and so on. Lots of bats and spiders and insects and so on. You can go in there and do an adventurous tour, but it's a bit smelly because there's lots of guano in there. Not from birds, but from bats. It could well be part of the same system as Harrison's Cave, but that's not been proven yet. And there are stories that maybe this was used as a refuge for runaway slaves during the sugar plantation era. Now, I mentioned the fact that there's very little surface drainage. Because there's very little surface drainage, in Barbados, you need to get the water from underground. So there's about 120 odd wells which are privately owned, where they pump up groundwater for irrigation, so water from under the ground. Now, water from under the ground, if it's come up through limestone, is great because it's kind of been naturally filtered. And that's why most of the drinking water comes from in Barbados. But if you look at the map there, you'll notice that about a third of those water wells for drinking water are marked in red, and about a third of them are by the coast. Now, what's significant is if you drill a water well, if you excavate a water well, before you start pumping out of that water well, you'll find that you have this kind of situation with the slightly less dense fresh water sitting on top of the slightly denser salt water. When you start pumping, the boundary between those two starts to get pulled up. If you think of it in 3 dimensions, it's like a cone. And that cone will migrate towards the well. Now, at this stage, no problem. You're still pumping fresh water. But when you get to this stage, you're sucking up some salt water into the well. And the human body cannot tolerate very much salt at all. So you've got a big problem. And once you've had this situation, what's called a saltwater incursion, it's very, very difficult to reverse, and you've reduced your water supply. When that becomes a really big problem is if you're also increasing your demand, which is what's happened in Barbados, as in many tropical destinations. So what's the solution? They were getting this problem with salty wells. So in 2000, they spent nearly $40 million on building a big desalination plant at Brighton. So what this does, it pumps up the brackish water, the water that's a little bit salty, from 10 wells. So they're all about 25 metres, about 80 foot deep, something like that. And in very simple terms, they heat up the water, they collect the steam, that then is condensed, and that gives you the nice fresh water, leaving all of the salt behind. And that provides about 20% of the water in Barbados. It is quite an expensive sort of water, but it works. But water's not the only thing underground in Barbados. In the central east coast, near the place called Bath, there's a petroleum seep near the beach. So you've got very thick, viscous petroleum. You might call it bitumen, to maybe familiar. You know, that's what they mix with gravel to put the surface on roads. It's quite a small oil field. You can see that the nodding donkeys, the pumps that are pumping about 1,000 barrels a day. And this provides perhaps 11% of Barbados's needs of petroleum. You can't use it straight away. It has to be refined. There's a lot more oil further south in the Trinidad region, so the oil from Barbados is sent down there to be refined. So how did this form? Well, remember the Scotland formation, the old rocks with all the sediment coming out of the Orinoco River. Well, some of those sediments were fine mud clays and shales that were rich in organic material. And when you get a shale rich in organic material being buried, because remember there was lots of compression, so as well as the land being pushed up, some of the rocks were being pushed down, and when you go down, it gets hotter. So if you heat up, and if you have a heat and pressure, then the organic material in this shale gets broken down. The big complex organic molecules are what's called cracked. They're broken down into smaller molecules, and you go through a sequence of going from the solid bitumen or tar, then going into a heavy crude, a light crude, eventually oil. And if you heat it up too much, you will get gas and then nothing at all. Now, we had the generation then of this oil, which is less dense than the other fluids in the rock, that are less dense than the water, so it rises up. And it rises up into a reservoir rock, which needs to be both porous and permeable. Well, what does that mean? It means that you've got a rock full of holes. And importantly, those holes are joined together. So do not imagine that an oil reservoir is like a lake of oil. It is not. It's a rock with all the holes in it, interconnected holes, filled in with the oil or the gas. And you might get maybe 10, 15% porosity. That would be really good. If you're on an oil rig, you'd be excited about that. Now, you don't want the oil or the gas to get to the surface as a seep, because then you're going to lose all of your gas. So in order for it to be trapped, you need an impermeable layer, a layer that hasn't got interconnected pore spaces. And that's what's known as a cap rock. And that very often is formed by the folding that I mentioned earlier. So you might get an upfold, an arch, what's called an anticline. And the oil or gas will be trapped at the top of that arch. And that's what you want to drill into. So, a few takeaways for you. First of all, the Caribbean islands are volcanic. It's a volcanic island arc formed by oceanic crust going underneath oceanic crust and partial melting producing andesite magma for nice explosive volcanoes. Secondly, Barbados is an exception. It is not volcanic. It's the BAP, the Barbados accretionary prism, where you've got this sort of wrinkling, if you like, of the crust due to compression of all of that sediment from the Orinoco. Thirdly, that the island has a stepped profile, which you might remember is from periodic episodes of uplift, creating a series of fringing reefs. That within, excuse me, within the limestone, we've got caves formed by weak carbonic acid dissolving the calcium carbonate to make the cave passages. And then the cave formations are formed when the water containing the dissolved limestone reaches an empty space, and because of the difference in the concentration of carbon dioxide, we get the precipitation of the stalactites and stalagmites. And finally, that the increase in tourism has led to some significant problems with water supply due to the saline incursion in coastal wells. And also that has been partially solved by the use of desalination plants. Now, I mentioned the oil. Well, future talks. I will be doing a talk called Memories of a Mudlogger. In a different life, many years ago, I worked on oil rigs. So in that talk, I'll be talking in a little bit more depth about the origin of oil and gas, about how it can accumulate in economic quantities, about how you can identify where those economic accumulations are, and how you go about drilling for them. So that's that one. But do check the Daily Times to check the time. And on the way back from the Caribbean, I will also be doing a couple of non-geological talks. So if you go on a cruise and you get home and people say, "Oh, how was it?" And you go, "Yeah, it was fine." It's not a very long conversation. But if, like Callie and myself, you were in the middle of the Bay of Biscay during Storm Ciarán and people go, "How was your cruise?" Boy, have you got a story to tell. And my premise for my talk on the way back, one of my talks on the way back, is that it's when the going gets tough that it makes a good bar story. When things don't quite go according to plan, when you get lost or chased or bitten. And that's happened to me quite a lot during my adventure travels. So that one is exciting, it's entertaining, and it's got quite a lot of humour in it as well. Now, you may have picked up on the fact when I was talking about caves in Barbados that I'm rather passionate about all things subterranean. So I will also be doing a talk which I call Mud, Sweat and Beers. So whether you love it or hate it, whether you've been caving and remember it and would like to be reminded, or whether you were a full-on caver back in the day, or if you never want to go anywhere near a cave but you're a little bit intrigued, this is for you. So lots of beautiful underground formations and quite a few adventures as well. So that leaves me with just saying that on the last couple of days of the cruise, I will be doing some more geology. So I'll be taking you on a journey to the centre of the Earth, looking at Earth structure. And to finish off, I'll be talking about extinction in my talk entitled Meteors and Dinosaurs. So thank you for listening. Thank you to the tech team. If you want to ask me any questions, I will be standing at the back outside. If you think of your question 5 minutes, 5 hours, or 5 days later, please stop me around the ship. There's nothing I like better than talking about rocks. Thank you.